Hi, this is a lecture on entropy and Gibbs free energy. So these are our learning targets. We're going to be able to understand what entropy is and then look at whether it's increasing or decreasing in any system. We're going to look at what the driving forces are and whether or not a reaction is spontaneous, and then ultimately we will be defining and calculating Gibbs free energy. So how do we know if a reaction is going to be spontaneous or not? So for example, if you guys use your thermodynamic sheet and you look up Ni3, the heat of formation is 154.4 kilojoules per mole. So think about, did we say that the positive or the negative delta H of formations were going to form more stable substances? So let me show you a little video of this compound.
It's always good to start a video off with a bang, and there could hardly be an easier way of doing that than with this stuff. What we have here is a contact explosive called nitrogen triiodide. It's a highly unstable substance that detonates when disturbed. Now, you might have heard of nitroglycerin, which is another kind of contact explosive, which goes off when you hit it with a hammer, but this stuff is in a league of its own. Even something like a mosquito landing on it will set it off. Now, the reason that
So very reactive and very unstable. So if you remember, if something has a negative delta H of formation, it's going to be very stable. And if it's positive or if it's not very, even if it's negative but not very negative, it tends to be unstable. So those are things that are, you would not want to travel in your car with any of those items. So we're going to look at what are the driving forces, in terms of reactions. How do we know whether a chemical reaction will happen or not, whether it's spontaneous or not? So the two things that we're going to be looking at that determine whether or not a certain chemical reaction occur are enthalpy, which we know about, and then entropy, which is something new to us. And there's a typo here. This should say entropy. So we know that enthalpy-wise, most reactions are exothermic. So that heat of formations, when you calculate the overall delta H of the reaction, it's going to be negative. But we know that endothermic reactions do occur too. And the only reason that an endothermic will happen, it's not as common, is because somehow you're increasing the randomness or entropy of the substance. So I will show you a video of an endothermic process.
What I have is some barium hydroxide. Okay, and I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now, what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk. Oh. I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, so I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second. So, I'm going to mix these two things together and carefully, I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to make it. Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. that sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well. So much energy has had to be taken out of the environment. It's got the water so cold that it's dropped below freezing and frozen onto the bottom.
How cold?
So that was a video of an endothermic reaction. So they do happen and they can be spontaneous. But in order for them to be spontaneous, we need to kind of be looking at what entropy is. So I want you to think honestly about your room, whether or not you find yourself in this room over here, or if you find that your room and eventually always ends up like this room. So this is just showing you a silly thing that it is natural for things to become more random. In order to have this room, which I know some of you do, you have to input energy. You have to constantly be putting things away, and over here, this is more natural, what tends to happen. And this is a universal thing, not just our rooms. Things want to become more random naturally. So that is what entropy is it's the measure of disorder or randomness. And if it's greater, it's a value, a number, and it's going to be a delta, a change in entropy. If it's greater than 0, that means entropy is increasing. That's what's kind of natural to happen. If it's less than 0, it's decreasing in entropy, and that's not as common. It can happen, and we'll talk about that. So if you think about the states of matter, solid is way more organized. This would be like the really clean bedroom, whereas a gas is way more random. So the entropy, as something changes from a solid to a liquid, it increases. It becomes more random. It gets even more random as I go liquid to gas. We can look at entropy in reactions too. So if you look at these 5 reactions, we can decide as the reaction progresses left to right, is entropy increasing or decreasing? And you can also think of it, do the reactants have more entropy or do the products have more entropy? So if I look at this first reaction, I can see that I have, we can look at the coefficients too. I wouldn't even need to this time though, because I have a solid on the reactant side, and over here I have gases and liquids. So the entropy is increasing as this reactions change into products. The next one, I have all gases. So now I would want to look at the number of moles of gas. So here on the reactant side, I have 3 and 1 for a total of 4 moles of gas. And then on the product side, I have 2 moles of gas. So this side with the 4 moles is going to be more random or have higher entropy. So the reactants have more entropy. And then if we go to the third reaction, this one, obviously these reactants have more entropy because you're forming a solid, plus there's more moles over here too. Number 4, you have to look at the moles. There's 12 moles of gas on the product side and only 6 moles on the reactant side, plus a solid, which doesn't have much entropy. So for this one, the products would have more entropy. And then lastly, this is going to lead us into what we're going to be doing next unit, is when we take an ionic compound and dissolve it in water, it becomes aqueous, AQ. So that increases in entropy too, because these ions now can, there's twice as many as there were when it was a solid. Another case where you could look at entropy is, I don't know if you've ever done this, but when I grew up, this is the kind of orange juice we got. It was frozen in a can because I lived in the country. We didn't go to the grocery store that often. So, and I buy this now sometimes too. My kids they don't have juice all the time. So sometimes we just take it out of the freezer and make it. So so what it is it's concentrate, and then you add cans of water to it to make it back into normal, like orange juice. Which one would have more entropy? Which would be more random? The concentrated version or the dilute, less concentrated? So if you fill this up with water, everything can move around in way more space and be more random. So the dilute solution is going to be higher in entropy than the concentrate. So in all, so far we've talked about entropy being positive or increasing is good. The universe wants this. Negative or exothermic reactions are also more common, and those are, so if I have something that's increasing in entropy and it's exothermic, it is going to be a spontaneous. It doesn't mean it's going to be an explosion, but that reaction is going to happen. If I have something that's decreasing in entropy, so it's getting more ordered and it's endothermic, it's not going to be spontaneous, no matter what. The question is what if I have the entropy saying no, it shouldn't happen, but the enthalpy says yes? Or I have the entropy saying, yep, this should happen and be spontaneous, but the enthalpy is saying, nope, endothermics are not as common. So that's where we get to something called Gibbs free energy. And Gibbs free energy is a calculation that we can do. And it's the letter G. And then, so we calculate the delta G, or the change in Gibbs free energy. If it's a negative value, then the reaction is spontaneous at that given temperature. So we can plug in the enthalpy value and then minus the temperature, which has to be in Kelvin, times the entropy value. And another way, so one thing I would add in this notes is that a negative delta G is spontaneous at that temperature. Positive means it will not happen. So it's like a tiebreaker. We know for sure if this is negative and this is positive, it's spontaneous, because you're going to have a negative and a negative, you'll get a negative answer. If this is positive and this is negative, this term becomes positive so that you get a positive answer. So the tiebreaker part comes in when you have the enthalpy saying yes, it should happen, entropy is saying no, or you have the enthalpy saying yes and the entropy is saying no. So that leads us kind of to this chart. So if the enthalpy is negative and the entropy is positive, over here, this is for sure spontaneous. If the enthalpy is positive and the entropy is negative, it's for sure not spontaneous. So the question is when you have the two, so when I have this and this, so I have a yes and a no, that's where we would plug it into the Gibbs free energy and see whether we get a negative value to know whether that's spontaneous. Same thing here. I have a yes and a no. So that when I plug those in, I have to see what the value of my G will be.